when we look in our agricultural systems, can you pick out the problem in this picture? How far down are the root systems of the crop, of that row crop going? They're only down this far. What's causing this problem? Can you see that black layer right along there? Plow layer. So as we've gone through there with the tillage equipment presses down at that depth, and it causes compaction. If you're compacting at that layer because you've pushed down on that as you're pulling your tillage equipment through the soil, water moving through that soil is going to hang up at that place. Water will not move through soil of one density into soil of a different density. It will not move. And so you're going to have waterlogged soil. If you get enough rainfall, your whole soil is going to puddle. So puddles are telling you, you've got a compaction layer down here. And we're going to have to talk about what is so wrong about compaction layers. Because we're going anaerobic, oxygen cannot move through here because the water backs up, cannot move, we're going to go anaerobic. That black layer shows you that. When we dug this pit, the smell coming out of here was like, oh, rank. A little bit of rotten egg, a little bit of ammonia, a little bit of vomit smell. Yeah, really fun when you mix the three of those things together. So, the other thing I like to point out in this particular picture is look at what's happened to all the calcium carbonate they've put into that soil over the last couple of years. They were told to put lime out here because the soil is extremely acidic. What causes your soil to be so acid? The anaerobic conditions. We're making anaerobic organic acids. That's what drops your pH. It's not a lack of calcium. It's the biology has been screwed up, and we don't want to be doing that anymore. So they were told every year for the last 32 years to go out and put 3 tons of lime and half a ton of gypsum on their soils every year for the last 32 years. The grower comes into my office with this pile of papers, and he just stomps right up to my desk, whacks this whole pile of papers out in front of me, and I'm sort of like, what have I done now? Oh, he's got a whole bunch of reports and they don't make sense to him. Oh, what am I going to do? And he says, I've been sending my soil samples into the University of California, Davis, and every year for the last 32 years, they've been telling me 3 tons of lime and half a ton of gypsum. And I sent my soil sample into them again this year, and they said 3 tons of lime and half a ton of gypsum. You know what? I don't think it's working. And me being myself, I'm thinking, slow learner, aren't you? Didn't say it. Zipped my lip. Okay, let's explain what's going on. Because what's causing this problem is not a lack of calcium in your soil. The calcium, 3 tons of lime and half a ton of gypsum, is going to neutralize that acid for approximately 2 weeks. And then the acid is back. How much good did spending all that money on that lime and the gypsum, what did that cost you? So lime, gypsum, don't. It's not going to solve your problem, and really what we need to do is solve the problem. And the problem is a lack of oxygen. We've got to get the biology back into the soil at that depth and rebuild the structure. We're going to have to get organic matter down here where this salt has been accumulating. There's no way there's any biology down here where, look at the calcium carbonate. Look at the gypsum. These are both salts. If perchance your roots could get through the compaction layer somehow, they're going to hit that salt layer. Woo! Not going to grow through that. So we have basically put our roots into a coffin. And then we wonder why we've got diseases and insect pests. Why they are not growing maximum yields. Rebuild that structure by getting the biology in here so the root systems of these crops can go down as deep as they ought to be going. And a crop like this should be putting its root systems down 8 to 10 feet through the course of that one growing season. I don't have to worry about summer water. So can we get going there? So I want to be really clear about the definition of soil. Because apparently, most soil scientists, my age anyway, have no clue what the actual definition of soil is. The father of soil science, Hans Jenny, the person who started the whole discipline, defined soil as being, the mineral component that comes from your rocks, the breakdown of your sand, of your rocks, your pebbles, your parent material, your boulders, into sand, silt, and clay. And what the fractions of each of these is depends on your parent material. So go back to your parent material and it'll tell you how much sand, how much silt, how much clay will that break down into. You want to know that information? You just go to the Natural Resource Conservation Service. You look up your parent material on your property, and you'll find that pretty much all of the United States has been done, except for some of the federal parks. So we've got all the minerals that you need in those sand, silt, clays, rocks, and pebbles. But to be soil, it cannot be just this. This, all by itself, is the 4-letter D word in soil science. Dirt. And so you have to say it just with that kind of tone of oh, it's disgusting. Dirt. It's dirt because it doesn't have any organic matter and it doesn't have any organisms. Well, if you have no food to feed the organisms, well, why would the organisms show up? Think about yourself. If we don't feed you 3 times a day, are you going to show up? So, got to have that organic matter. We have to have the organisms to be soil, to build structure, to protect our plants, to do nutrient cycling, to decompose toxins. We have to have the life in the soil. So when we look at the mineral content, here we are. This is the table that is in some form or another, different soil chemists doing this work. So it kind of depends on exactly which book you're looking at. This comes from Brady. There's the average value of all these nutrients within your soils. And all 107 elements in the periodic table are actually, I just took the first page. But take a look at calcium in your soil. Is there any reason to put lime and gypsum? You've got 15,000 parts per million calcium. In every teaspoon of your soil, you have way more calcium than you could possibly use. Why do we think that our soils, that our plants are lacking in calcium? There's plenty of calcium in your soil. Get it out of your soil. How about nitrogen? Here we are down here. 2,000 parts per million on average. Here's the actual range. 200 to 5,000 parts per million nitrogen. That's the worst soil on the planet, and it still has 200 parts per million. Those are micrograms per teaspoon. In every teaspoon, you've got more than enough nitrogen to grow your crops in your field. So why are we adding more? Because we've been told you don't have nitrogen. You've been told you don't have phosphorus. How many have been told that one? Yep.
If you're in dirt and not soil.
If you're in dirt and not soil, you still have the nutrients. This is dirt. You have all the nutrients you require. It's just not in a plant available form. How are you going to get these not plant available forms converted into a plant available form? Yeah, put your life. Get the organisms, the food web. So stop believing it when the fertilizer salesman says to you, oh no, you don't have enough phosphate in your soil. We're running out of phosphate fertilizers and the government's going to have to pay billions of dollars so we can develop a method to extract phosphate out of the rocks, the pebbles, the sand, the silt, the clay, and sell it to you as phosphate fertilizer. Instead, put your own workers back to work. Get these organisms to take the nutrients. So this is kind of a different representation of the last chart. Here's the total amount of any one particular nutrient. It is the bacteria, fungi, being eaten by protozoa, nematodes, microarthropods that are releasing exchangeable nutrients that sit on the surfaces of your sands, your silts, your clays, your organic matter, and your organisms. And it is these same organisms that produce the soluble, inorganic forms of those nutrients. The Problem with the chemical world is the only thing they've been telling you about in your soil chemistry reports is this little tiny pool down here. That's all they tell you about. 4 bases, so base saturation, all you get told about is that pool right there. But look at what you actually have in your soil. You have hundreds of thousands of years worth of nutrients in your soil. Why are you putting on more? Who's making money? If that fertilizer salesman can convince you that you've got to go out and buy, if somebody convinces you you have to go out and buy compost to put these nutrients back into your soil, what's really important about compost? Not the fertilizer that's in it, it's the life that's in it. Because you got all the nutrients that you need in your soil. None of your soils lack those nutrients. So when you get convinced, I'm going to have to go and I'm going to have to buy something, I'm going to have to buy these amendments, rock dust, I got to put out some kelp, I got to put out this and that and the other thing, I got to put manure on. So, you put some of those things on, especially manure. What's wrong with manure? High in salts. Okay, you're just killing the biology in your soil when you put straight manure on your soil. So then that means the next year you're going to have to go and you're going to have to get some more fertilizer, some more manure. And the next year you're going to have to put some more on. And then the next year you have to put more on it. And isn't that the definition of a moron farmer? Don't go there. Because you need to keep the money in your pocket, not be giving it to somebody else. Your compost is for the organisms. Your soil already contains the nutrients your plants require. Another way to do this, I like to show this one because down here we have some of the different extracting agents that we use to extract these nutrients out of the soil, the chemical extracting agents. The point I want to make is that if we're doing the actual total, there is no way to extract all of the nutrients and really get the total amount of nutrients. Our chemistry just isn't that good yet. So if we grind the soil, we use concentrated nitric acid or concentrated sulfuric acid, and turn all of those nutrients into a soluble form, and then combust it using a gas chromatograph or a mass spec, we would get this value right there, and a little bit less than the actual total. If we use less concentrated acids, we're going to get a little less extracted. Okay, so you got to start understanding what your chemistry lab is using as extracting agents so you can interpret what your number means. Is it really good, or is it just because they use a much nastier extracting agent? Here we are in the exchangeable pool. So when you're looking at the Albrecht approach, that's exchangeable pool. What's your calcium-magnesium ratio? Well, which extracting agent are you using? Because if you use a malic 3, your values are going to come out way higher than if you use a Bray 2. Not nearly as high. This is an Albrecht extractant. Quite a bit lower. So which one's truth? How many of your clays are actually going to be flocculated because you've got those exchangeable calcium and magnesium? Well, it depends on which extracting agent you use. How many different extracting agents are actually on the books? Different soil chemistry labs use different extracting agents. Which one tells you the truth? There is no relationship between what's going to happen to your clays and any of this information that's coming from your cation exchange capacity, from your base saturation. There's no relationship to how much your soils are going to flocculate. Isn't that interesting?
What's flocculate?
What's flocculation? Thank you. I sometimes forget scientific, Like what? You don't all know this? Yeah. Well, I'm teasing you. Because, it's not one of those things. When you don't have enough calcium, too much magnesium, not enough calcium, most of your clay platelets are going to be collapsed. They're going to be a column of clays that are just completely compacted down together. So every single clay platelet is just, there's no space for oxygen or water or organisms. Nothing can fit between those clay platelets. Now think of this in a three-dimensional form. We got a column of clay platelets, there's another column, there's another column, there's another, all just completely packed in. When we don't have adequate calcium, too much magnesium, not adequate calcium, our soils are going to be compacted. There's no way not to be compacted. So water moving through your soil is going to stagnate at the top of that layer and then either go sideways down the hill or cause your soil to go anaerobic, and now we got compaction problems. So if you want to flocculate those clays, if you want those clays to open up so you can get oxygen and water and organisms in your soil, so we can actually make this soil, we've got to increase the concentration of calcium in here so that each one of these clay platelets repels each other. So when they repel each other, they do this. And then the next one's there, next one's there, the next one's there. So all of a sudden we've got all kinds of air passageways. We've got all kinds of ways that water can move through that. But what really brings the calcium into that compacted clay column? If you put a lime on the surface of your soil, you're just expecting it to run on down. The calcium's going to run into the compacted soil by being carried by water. Wait a minute. Remember what we said? You can't get water through here. There is no space. There is no way. So your calcium carbonate just dissolved in that water is up here. And it's going to end up somewhere you don't want it. It's not going to do you any good. So how do you actually get that calcium to get in between each one of those little clay platelets? And that's what fungi do. So fungi, their little hyphae, move in between those individual clay platelets up here at the top. And because fungi, many fungi, have oxalate crystals on their surfaces, and they've got lots of calcium on the attached to those oxalate crystals, as that fungus grows into that clay, through those clay columns, it's releasing the calcium, and the clay goes boing, and now you got space, and the fungus now starts growing, and it pushes its way into the next little bit, and the clay colloids.
Are the hyphae
The hyphae are the strands of the fungi. Yep. Miles, yeah. Yeah, so we got to have the right biology in there. For us to do anything in soil, for us to fix any of this, we have to have life. Now, let's keep going. Here's your soluble pool, and you're going to get way higher numbers of soluble nutrients when you use a coal well as compared to a Bray Olsen or a Bray 1 or a Melick 1, way less. Well, let's use a Morgan. Yeah, Morgan's not much different than water. Potassium chloride, a universal buffer. Yeah, pretty much kind of like water. So tell me, we're asking what the soluble nutrients are. What nutrients are in solution, in the water solution? Why don't we just use water? How many different kinds of extracting agents are on the books? Did I say what it was for the exchangeable? There's about 1,000 different extracting agents on the books. There's about 650 different extracting agents when we start looking at soluble nutrients. Which one tells you truth? None of them. None of them. Maybe water for here, maybe. But it's not a good correlation. So really what determines whether your plant is going to get these nutrients or not? It's life. Do you have the nutrient cycling happening or not? So why are you sending samples into a soil chemistry lab? What possible use is it? You're making them rich, and you aren't. So what should we be measuring? Let's be perhaps looking at these different nutrient pools. I talked about total nutrients, exchangeable, what's bound to the surfaces of things, soluble, dissolved in water, and then what's actually in your plant. That's probably what you should be testing on occasion. Is your plant actually getting the nutrients that it needs from the soil? And if your plant doesn't have an adequate set of nutrients in its tissue, then you better get the right biology out there to fix the problem. Going out and putting on inorganic fertilizers, going out and putting on organic fertilizers, are those nutrients actually going to get to your plant? And how could they if you don't have the right biology? So, why would there be a need to... I always like going back to the Green Revolution. How is it that when you put an inorganic fertilizer out, when the conventional world, when you put out manure and you see the plant starting to grow faster, and I suspect many of you have seen that, what did you actually add back into the soil that made a difference? Life. It was life. If we put out an inorganic fertilizer and we see our plant grow better, well, that's just telling you don't have the life in that soil. So get those organisms back into the soil. So now think a little bit about the transition. If we've done things through no fault of our own, we believed people that wanted to sell us something that we didn't need. We believed them and we put that material out and the life was harmed. You can't stop using your amendments until you get the biology back in your soil. Because, if you don't get the biology back in the soil, your crop is going to suffer. So, back off on the amount of amendment by 50% in this first year. And then start putting the biology. Make sure your compost is actually compost. It's aerobic. It has the organisms in it. So how do you know whether Patrick's compost is any good or not? Microscope. Take a look at what's in it. And then that tells you if you do want to buy it. And hopefully he's got that data for you. That he can tell you exactly what the life is in that compost. So, nutrient cycling, we've talked about these things. If the organisms aren't present, you need to put them back so you can get the results that you want with your plant material.